Hi, everybody. We're almost about to wrap up the electricity unit, and we're almost at spring break, and I'm looking forward to it. I need a little break from all this. Um, I just want to go through the worksheets 18.03, which are all doing, and then 18.04 is one that you're working on together as a group. I've broken into two parts. But what I'm going to do today in today's short video is sort of walk you through it just to sort of show you how, and do a couple of sample problems from both 1803 and 1804. For 1804, you can work on it with your lab partners, and then you can everybody in your lab partner group can actually turn in the same worksheet. But I'd like you each to turn it in just so it's easier to grade and give responses as well. So take a quick look at this one. This is from 18.3. 360 watt 120 volt light bulbs are connected across 120 volt power sources shown below. Find the following. The normal resistance of the bulbs. So we know the power of the light bulbs, and we know the voltage. So I would probably use this equation, which has voltage in it, or this equation. In this case, though, because we're looking for resistance, I'm going to use this one right here. And if I do that, backwards, I get the power is 60 equals voltage squared over the resistance, and I'll discover the voltage of each bulb is 240 ohms. So that's the answer to the first part, and I wrote it down here as well. And now let's go ahead and analyze the circuit. Once you know the resistance, the very first thing you do in every circuit problem is figure out the total resistance. In this case, I've got two 240 ohm light bulbs in parallel. If you calculate that, the equivalent resistance of these two is 120 ohms. And then that is in turn is in series with this light bulb, which is 240. 240 plus 120 should give us 360. And so the current in this circuit is voltage over the total resistance, should be 1/3 of an amp. And all of that has to flow through this light bulb. So that part I know. Now after this point, it's going to split up. Part of it's going to flow straight through this junction. Part of it's going to go this way. Now some of you might intuitively say, oh wait, it's obvious what's going to happen, but let's walk it through just in case it's not obvious. What do we do next? Let's take a look at the potentials. So I'm going to define this point down here as 0 volts, which automatically makes these 2 points 0 volts as well. Remember, there's no voltage changes across the wires. And up here, that's 120 volts. And now what's the voltage drop through this light bulb? Well, remember voltage drop is I times R, so 1/3 times 240 is 80 volts. So delta V across this light bulb is 80 volts, which means what's the voltage going to be after I go through it? If I was at 120 volts and I lose 80 volts, 120 losing 80, this point over here should be at 40 volts, and that point also as well, which means I can now answer this question up here. What's the voltage drop across this first light bulb? The answer is 80. It goes from 120 to 40. And now for these two light bulbs, they both go from 40 volts down to 0 volts. So what's the voltage drop across both of these? The answer is 40 volts. The current for each bulb, I already know the current for the first one here is 1/3. How do I figure out the current for these two? Well, I know the voltage drop is 40. I know the resistance is this. And again, if you remember, the voltage change across any resistor is just equal to, oh, that's really bad, is equal to I times R. That's the voltage drop. That's the resistance over here. That's a delta, believe it or not, which means you can very quickly calculate that each one of these is 1/6 of an amp, which means I can go back over here and put in these two answers 1/6. Finally, part D, what's the power delivered to the three bulbs? Because I know the voltage change across each bulb, and I know the current, I'm going to use I times V. Yes, I could also do I squared times R, or even V squared over R. All of them would give the same answer. I'm just trying to do the simplest I can possibly do here. So that's the power through the delivered by the first bulb. And then the other two bulbs, I've got 1/6 of an amp, and the voltage change is 40. So that gives me 6.67 watts and 6.67 watts. Notice that though, even though the current's half as large, the power of the bulb is actually 1/4 as large because the voltage drop is also half as big. So the current is half as large and the voltage change is half as large compared to this bulb here. So remember these powers because we're going to look at it in this next circuit, which is going to be a little bit more interesting. So in the second part of this, light bulb R3 is now removed. So boom, it's gone. So now what happens to the brightness of these two bulbs? And to solve that, let's go, before we answer that, let's take a look at these questions down here. First of all, what's the total resistance of this circuit? Well, you should see that it's 480 ohms. I'm going to use my finger to draw this because it's just too slow. And so the current in the circuit is going to be 120 over 480. And hopefully you can see that it would be 1/4 of an amp. And that current is going to go through both these bulbs. So the current through this one's going to be 1/4 of an amp. And because there's no other route for it to go when it gets to this junction over here, the current through this one's also going to be 1/4 of an amp. Now, what's the voltage drops? If you quickly work it out, assuming I start at 120 volts here, the voltage drop across the first light bulb is going to be 1/4 times the resistance, or 60 volts, which means by the time I'm over here, I'm at 60 volts. And you can also realize I have to be down at 0 here, or you could realize, oh yeah, the voltage drop across the second bulb is also 60, assuming that's 0 volts. So I've answered both these questions. The potential difference across both these bulbs would be 60 volts each. The current for each one of these is also going to be the same. It's going to be 1/4 of an amp through each. Sorry, I should write it out for each one of these, but my pen is acting so slowly, I'm going to work this way. And the power delivered to each one is just going to be the voltage across it times the current, which hopefully you can see very quickly here is going to be 15 watts for each one of them. So what happened to the brightness of the bulbs compared to what they were before? If you remember before, this one was about 26 watts, and these were about 7 watts. So what happened to the brightness of the first bulb? It decreased, which is my fast way of writing it. And what happened to the brightness of bulb 2, R2, it increased as we did this. All right. A circuit consists of 3 identical light bulbs, each of resistance R, connected to a battery of potential E as shown above. Calculate the expression for the equivalent resistance when the switch is open. All right, when the switch is open, this is air, so it's got to go through all 3 of these before it goes back. And so the total resistance just R plus R plus R, or 3R. If the switch is closed, the current's just going to go through these 2 bulbs and then straight back this way. It's going to go through this path of least resistance. No current at all is going to flow through the light bulb over here. And the resistance just becomes the first 2 light bulbs, A and B together, which is 2R. Write an expression for the power supplied from the battery when the switch is open. So power can be written a bunch of different ways, but because I know the voltage and the resistance, I'm going to just do the V squared over R1, which in this case the voltage is the EMF divided by the resistance 3R. And for the second one, it's going to be very similar, except in this case, it's going to be the EMF squared over 2R. Using the results already explained, what happens to the brightness of the bulb when it's closed? So, when it's closed, let's think about this in a couple of ways. So, when the switch is opened, each one of these up here is going to have a voltage drop of the EMF over 3. Sorry, I should have written this. This is the voltage change, because they all should be the same. EMF over 3, voltage change. Sorry, my pen is, I got to work really slowly, is EMF over 3. And the current for each one of these is going to be the EMF over 3R. So initially our power is going to be, if you look at this, the power for one of these bulbs is going to be the current, the EMF over 3R, that's that, times the voltage, which is the EMF over 3, which gives us EMF squared over 9R. Now, I want to show you that real quick. You might say, wait, I thought we said the power delivered by the battery was EMF squared over 3R. Yeah, this is the total power delivered by the circuit. The power for each bulb is going to be 1/3 of that. So that if you divide it by 3, it tells us the power for each bulb, which is going to be what we just found, the EMF squared over 9R. So what do you think is going to happen here if it's only going through 2 light bulbs? That power is going to be divided between the 2 bulbs, which means we have the EMF squared over 4R. What's going to happen when you close the switch? The power delivered to bulbs A and B is going to increase, go from EMF squared over 9R to EMF squared over 4R. So A and B are going to get brighter than they were before. A and B are going to increase, and C is going to be completely off when you close the switch. And my apologies for my horrible pen. All right. Write an expression for the current for each bulb when the switch is open. Oh, we did a bunch of this already. A potential difference, we did that. We didn't do when it was closed. I'm going to skip this one because I basically covered all of it. I guess I can do the bottom one here. The current for each one when it's closed, the total resistance of the circuit, if I close this switch, is just going to be 2R. So the current for these 2 bulbs each is going to be the EMF divided by 2R. The current through bulb C is going to be 0. The potential difference across A and B is going to be the EMF divided by 2, and the voltage across C is going to be 0 because none of it's actually going to go through it. There's no current through it. So you can kind of see it. And we already talked about these up here. The potential difference across all of these are just the EMF divided by 3. And the current for each bulb here is just going to be the total voltage divided by the total resistance, 3R. Okay, sorry. All right, now this one. In the circuit at right, the voltage across resistor 1 is X times the voltage across that. Write an expression in terms of X and V for the voltage across each resistor. All right, so, I don't know, let's see. So if I I'll call this V2 as the voltage drop across this resistor. So the voltage drop across this resistor has to be X times V2. Does that make sense? It has that much more? And the sum of these has to add up to V. All right. All right, write an expression for the voltage across each resistor. All right, so let's do the easy one first. For R3, the voltage across R3, it's connected directly to, if you look at it, the battery. That makes it super easy. The voltage drop across resistor 3 is simply equal to the voltage. But now I've got to figure out what in the world is happening here. Well, the voltage drop across these two depends on the current. And so the current through 1 and 2 is going to be equal to the battery voltage divided by the sum of their resistances, R1 plus R2. And the voltage drop across resistor 2 is just equal to the current through resistor 2, which we now know is equal to this. Oh, this is going to be a bit ugly. Times its resistance R2. So we know what that is now. Okay, so wait a second. So we can actually figure this out then. Oh wait, once we know that, oh, this is easy. So the voltage drop then across resistor 2, we just calculated it. is VR2 over R1 plus R2. And what's the voltage drop across resistor 3? It's X times that. So I'm just going to write it as X V R2 over R1 plus R2. This is a little bit strange. I should say I actually should write delta V on or across. I'll just say on. These are all the change in voltage across each one of these. It's not really the resistances. It's their voltage change. And so this is all, oh wait, can I leave it that way? For the voltage across. In terms of X and V, well, yeah, I've got to know the resistance. Okay, I think that's as far as I can take that one. That one's messy. I'll admit it. And then let's take a look at these real quick. Sometimes, in this case, we're trying to analyze these circuits. And sometimes you're just like, well, how do I even analyze it? You can sometimes just, if you know all these are identical, let's just pick our favorite resistance. In this case, I'm going to go 2 ohms for all of these. Why? 2 ohms is nice because I can see I've got bulbs B and C over here in parallel. So when I put these 2 ohms there, and then I can actually solve a few things. Let's make the battery voltage 12 volts. And now we can actually solve a bunch of things on this. Here is, we can do the potentials around the circuit. These are 12 volts, 12 volts. And down here, this is 0 volts, 0 volts, and 0 volts. Oh my goodness. I'm going to go back to my trackpad. 0 volts. Once we do this real quick, we can do some quick current calculations. Let me show you. What do we know is true here? If you look at this part of the circuit here, we've got a 12 volt potential difference of across a total of 4 ohms, these two in series with each other. 12 volts over 4 ohms means that the current for each one of these is going to be 3 amps. And the current for this one is 3 amps. And they tell you in this that you can just use the currents to approximate the brightnesses, which I guess is okay. We'll talk about that. And then this one, these two 2 ohm resistors in parallel are equivalent to 1 ohm, which is in series with this 2 ohms. The total resistance of this whole section is 3 ohms. If you hook 3 ohms to a potential difference of 12 volts, you'll discover that the current's going to be 4 amps. And now let's figure out what the voltage drop is going to be. The voltage drop across this light bulb is going to be 8 volts, which means by the point I'm down here, I'm down to 4 volts. And you can very quickly realize, hey, if I've got 4 volts across 2 ohms, the current for each one of these is going to be 2 amps. The cool thing about electric circuits is you could do this other ways as well. I could have also realized, oh, wait a second, the resistance of these 2 paths are equal. Therefore, the 4 amps up here is going to split up equally when it reaches this point, but it'll work. But now let's go ahead and analyze the power in each one of these light bulbs. And I'm going to use the power is equal to I times V. So the current times the voltage drop. What's the power in this one? Well, the voltage drop is going to be, I guess I could just do I squared R maybe. Might be faster in this case, because I know the currents for each one and I know the resistances. Using the numbers I have here, 3 squared times 2 gives us 18 watts for this bulb, is how much power it's dissipating. That's related to its brightness. And this one's going to be 18 watts as well. Over here, I squared 16 times 2 is going to give me 32 watts. Interesting. Wait, did I do that right? Yeah, I guess so. And then over here, I squared 4 times 2 gives us 8 watts in each one of these. So when you rank these down below here, according to their power, let's see, would have worked if we had simply ranked them in current? Yeah, it would have worked as well. Which one's the brightest bulb? A is the brightest, followed by D equals E, followed by B equals C. And hopefully you're feeling pretty good about it. And now let me move into worksheet 18.4. Take a look at this. First of all, figure out, okay, in the circuit, find the current for each resistor, the voltage across each. So what we're doing here is similar to what we did before. And I just want to show you this real quick. So first of all, these two in series is 12 ohms. And then that is in parallel with the 6 ohms at the bottom. And it's not intuitively obvious, first of all, when you look at it. But this is then in parallel with this 6 ohm down below here. And if you do that real quick on your calculator, 1 over 12 plus 1 over 6, I should be able to do this in my head. Oh, yeah. The total of these two together then is just 4 ohms. So what's the total resistance of my circuit? Well, all of these three resistors down here are equivalent to 4 ohms, which is in series with this 8 ohms. The total resistance of my entire circuit is 12 ohms. So what's the current going to be flowing out of the battery? The current flowing out of the battery here is going to be equal to V over R, or in this case, 9 over 12, or you can reduce that, I guess, down to 3/4 of an amp. We know that all of that current has to go through the first resistor. So now we can do some quick calculations. Once we know that, we can do some amazing things. So we're still at 9 volts right here. We know that the current through this resistor right here has to be 3/4. So 3/4 times 8 gives us 6 volts, which means by the time we're down to here, we're at 3 volts. We've lost 6. And again, we know we're over here at 0 volts. Once we have that, we can very quickly do some calculations. There's a 3 volt potential difference across this 6 ohm resistor, which means the current through this one has to be 1/2 of an amp. And that means if you look at this junction, we've got 3/4 of an amp going in, 1/2 going this way. You could have also calculated it by taking the 3 volt difference across this 12 ohms, but you'll discover that the current going down this way is 1/4 of an amp, and that's the same through each one of these resistors along this path. Once we have that, we can solve all of this. We know the voltage drop across this resistor is 6 volts. Across this one is 3 volts. If you calculate it through this one here, that's a 1.5 volt drop, 6 times 1/4. And that means at this point in the circuit, we're at that. And by the time you're back over here, you lose the other part there. So the current for each one of these we've got written down, and we can calculate the voltage drop. I don't want to write it right now, but 6, 3, 1.5 volts, 1.5 volts. Oh, and that's it. All right, sweet. So I've done a couple of problems already for worksheet 18.04. The rest of these are working with your partners. Technically, this is not due until after spring break, but I'd recommend that you get a little head start on it so you're not struggling with it afterwards. I'll leave the due date kind of open. The other thing I want to mention real quick is on the AP Classroom, I'll start opening up Unit 1, the multiple choice and free response questions. That'll be your homework for after the break, but I wanted some of you to at least get a chance to start on it. We'll spend most of the month of April reviewing for the AP test, so we'll talk about that more in a little bit. With that, have a great night, and talk to you soon.